Hi there. This presentation is entitled 5 Steps to Deploy 1588 version 2 for LTE Synchronization. Welcome to this presentation from Calnex Solutions. The 5 steps to deploying 1588 for synchronization in your LTE networks are summarized as follows. First, determine the synchronization needs and the ITU-T network models for your network. Whether the network requires frequency only or frequency and phase and time, as well as we'll look at some of the ITU-T models that are recommended for deploying synchronization using 1588. The second step is to check the current network that you have. Is it ready for LTE? Third, we then determine the synchronization SLA parameters. We use lab tests really with the end goal of determining the parameters which you will use in your network for either the access network vendors or the equipment vendors, and to test the stability of your network in operation. Ultimately, you want to get pass-fail conditions for stable frequency and accurate phase and time in your network. So once you've done the lab tests to determine these parameters, you can then deploy 1588 into your network according to the ITU-T models. And once you've deployed, you can test and proactively troubleshoot in your network against these SLA parameters which you established back in step 3. So we'll look in a bit more detail at each of the 5 steps in the following slides. Step 1. Determine the requirements of synchronization and the relevant ITU-T model. What kind of synchronization is needed in your network? Well, fundamentally in the mobile network, the synchronization that's required is determined by the radio technology itself. With LTE, the frequency domain FDD LTE technologies require frequency synchronization, whereas the TDD technologies require both frequency and phase synchronization. But interestingly and importantly, LTE advanced features, for example, coordinated multi-point comp, network MIMO, will require both frequency and phase synchronization. So one of the first things to consider is, in your LTE deployment, do you need just frequency or will you need both frequency and phase? Also, even if you need frequency today, if you have plans to deploy LTE Advanced, do you then need frequency, and you will then need frequency and phase. So let's start with looking at the ITU-T models for delivering frequency and phase using 1588. The first thing to understand is that the ITU-T specifies some framework hypothetical reference models, or HRMs. The first is a network using only optical connections with up to 10 switches, which is called HRM1. HRM2 is a network which is a mix of a packet network, here specified 5 optical switches, with a mix of access technologies, a variety of microwave, GPON, or DSL technologies in the access. So depending on which of these flavors of networks is deployed in your mobile backhaul, whether it's an all-packet network end-to-end or a mix of a packet network and a different access network, these relevant HRM1 and HRM2 models apply to your network. So once you've determined which is the HRM model that applies to your network, we then look at the different ITU-T recommendations for deploying 1588 for frequency and phase. The first thing to note is that the ITU-T has different recommendations whether that network is going to be used for frequency deployment or for phase. For frequency, the G8265.1 recommendation talks about having a primary reference clock or a grandmaster in the core or the edge of the network, and slave clocks at the end of the network in the access points. For example, built into the node B or in the cell side routers. So this is fundamentally an end-to-end 1588 deployment where there is a grandmaster, no 1588 support in between, and 1588 support in the slave clock right at the end of the network. Now 1588 in these networks can be delivered through a variety of technologies. The core could be an MPLS core, or it could be OTN or Ethernet over SDH. The edge network could again be the same technologies. And then the aggregation points could be aggregation points for different access networks. MPLS, Carrier Ethernet, PON, microwave, DSL, and so on. They all apply depending on the type of network that is deployed in your network, the type of technology that's deployed in your network. 1588 can be delivered across this network with full frequency by installing a grandmaster and a slave. And in fact, today, many 3G networks already run 1588 by deploying a 1588 grandmaster or a number of 1588 grandmasters and 1588 slave clocks at the node B or in the cell-side routers. And that deployment is based on rules defined by the G8265.1 recommendation from the ITU-T. So the previous diagrams that we saw were really ITU-T recommendations for frequency. For deploying 1588 to transport phase and time, there are different challenges that have to be catered for by the ITU-T models. And one of the key recommendations from the ITU is to use 1588 aware equipment between the grandmaster and the end slave or application. Now this is known in the technology as on-path support. On-path support means the use of boundary clocks or transparent clocks, which are fundamentally 1588 aware devices in the core of the network. And how that looks in a real network is governed by the 8275.1 recommendation. Again, you fundamentally have the same network as before with your choice of core, edge, and access technologies. However, the big difference now is that you must have 1588 what's called on-path support, meaning that these devices in the middle of the network are no longer just ordinary switches or routers. They are what's called boundary clocks or transparent clocks. So in other words, a network that is today being used to deploy and deliver frequency synchronization using 1588 must have a level of upgrade to support phase and time synchronization for 1588 by adding boundary clock or transparent clock functionality. So in summary, the 8265.1 and 8275.1 recommendations from the ITU-T define the layout of the network models for frequency and for phase time respectively. Which model you deploy depends on what is the requirement of synchronization in your mobile network, whether it's frequency only or frequency plus phase and time. So once you've determined what is required in your network, the second step is to check what the condition of your current network is. In fact, very often when migrating to LTE, a network operator already is running a 3G network with Ethernet backhaul. And you may also be running 1588 in your network already. However, that doesn't mean that the network's working today for 3G and it will automatically work for LTE. So what do we need to do to check what the current network performance is and how that will relate to deploying a future technology in that same network? Well, the first thing to do is to really characterize the network. If you have 1588 running in your network today, or even if you don't, if you have an Ethernet backhaul network, you should go in and characterize the packet delay variation. You now analyze the forward and the reverse packet delay variation of the 1588 in your network. And this is useful for two reasons. One is it will allow you to characterize the network today, but more importantly, you now have a profile of your network which you can then use to test whether that network will support LTE in the next step, which are lab tests. So the first thing you should do is you should capture the 1588 packet delay variation in the current network at the existing cell sites. If you have 1588 running, you can run a capture using the Paragon M product. If you don't have 1588 running, you can have a test slave installed and capture again with the Paragon M product from Calnex. And now you have a profile of your network which can be used for the LTE tests in the next step. So importantly, determine what kind of technology is needed, and step 2, characterize your network today. Step 3 is then to go into the lab, and it's an important, vital step to do lab testing before you go and deploy this in the network. And the reason is, with the lab testing, you can actually determine the SLA parameters that are required for your network. Now, why is this unique and important 1588? The main reason is every 1588 slave clock operates with a different algorithm. Now, the problem is you cannot therefore have a standard set of rules in your network to deploy a slave clock from vendor A and a slave clock from vendor B. You need to take those slave clocks into your lab and determine the sync SLA parameters for that slave clock. Let's explain what we mean. We have a variety of vendors that play in the space of mobile backhaul today. So different equipment vendors that play in the core, equipment vendors that supply the primary reference timing clock or the 1588 grandmasters, and then vendors that have equipment in the aggregation and the access, as well as the node B portion. Now, all of these vendors potentially have different 1588 devices. Each of these may behave differently. So the big purpose of the lab test is to qualify the performance of each of these equipment that you are going to use in your network, so then you have a set of rules to test the network performance in the future. And that lab testing flowchart really involves 3 steps. You do the lab testing, you then use that lab testing to define your SLA parameters, and then in the network, you can monitor and test your network according to the SLA parameters. Why do you have to do the lab testing? Once again, there isn't a universal set of sync SLA parameters today. You need to establish the sync SLA parameters for your network for your slave. And once you do this, if you take this step, you then have a well-defined test suite to run on your network and for your vendors to run on their equipment before it turns up and ongoing in the network itself. And what are you doing when you're doing these lab tests? Well, for frequency, you are testing that the recovered frequency is stable according to the ITU-T masks. ITU-T G8261.1 defines a mask for maximum frequency error. So in other words, you're running your lab test to make sure that the recovered clock is within the 8261.1 mask. For phase, this is really determined by the cellular technology itself. So for example, time domain LTE has a specification or requirement of 3 microsecond intercell or cell to cell phase accuracy, which means that you could measure the individual phase accuracy at a single site to 1.5 microseconds. So in the lab test, you are testing that the recovered clock has a frequency stability according to the ITU-T masks and a phase accuracy according to the limit specified by the end application. So what do you do? Well, fundamentally what you do is you emulate the network. You emulate the network and you test the slave. So the Paragon X product from Calnex emulates the packet network, and it can emulate the G8265.1 network for frequency, or it can also emulate your current network. Remember, you have captured this in step 2. You've characterized your current network, and we can replay that exact profile back in the lab using the Calnex Paragon X. You would then play that profile into the slave and measure the recovered clock. So in other words, you use the Paragon X to emulate either the ITU-T hypothetical reference network and also your current network, and you measure the recovered clock to see whether it meets the limits. And that's for frequency. For phase, the 8275 network, again, the Calnex Paragon X product does exactly the same thing. It can emulate an 8275.1, which means an all-boundary clock network, and you measure the 1 PPS output to measure the phase accuracy. Again, you can also emulate your current network, because we've captured this in step 2. So we emulate the ITU-T network, and we emulate your current network, and we check the performance of the slave. And that's what we do during lab tests for frequency and phase. Now ultimately, the network profiles for 8265 and 8275, as well as your current network profiles, which you've replayed, will have associated with them what's called packet metrics. The packet metrics are an evaluation of the PDV into a analysis format determined by the ITU-T. So you would run those profiles and you would look at the packet metrics of those profiles. whether those profiles are the ITU-T profiles or the profiles you've captured from your own network. Now, if the slave clock fails the limit, ultimately it's a simple step of saying that slave clock is not recommended for that application unless you change your network. If it's very close to the limit, the packet metrics that you have from that lab test can be used directly as your network SLA limits. If the slave clock recovered clock is well below the limit, you can scale the packet metrics and establish your sync SLA limits. So just to summarize, we do the lab tests with stressing the slave clock using a particular set of packet metrics. If the slave clock fails, that slave clock is not suitable. If it's close to the limit, those packet metrics can be used at the same network limits, because in the network, if the network performs to those packet metrics, the slave clock will also recover the clock within the limits. And if your lab tests show the slave clocks recovering well below the limit, we can scale up the packet metrics and establish the network limits. And what we have by this is ultimately we have pass-fail limits for the network as well as the slave clock. And this is a far more valid method than using test slave clocks when testing in the network. You cannot use an emulated slave or an alternative slave in the network when you're characterizing your network for LTE. This is because, remember, we've said before, every slave is different. If you use a slave from vendor B to test a network which is then going to use vendor A, those results won't be valid anymore. Whereas this method of doing the lab tests and establishing the sync SLA parameters is a more valid method for establishing sync SLA limits for your network. So we've established the sync SLA limits for the network. Now we can deploy according to the ITU-T models. And just as a summary, we have the 8265.1 reference model for frequency and the 8275.1 reference model for phase and time. So we've done the tests, we've established what slaves we're going to use, we've established the SLA parameters for the network, and then we deploy in the network. And of course, finally, once we've deployed, we want to monitor and test against that sync SLA in the network. So we can do this by making measurements in the network. The Paragon M product from Calnex makes measurements and comes up with the packet metrics. Remember, these packet metrics tell me what is the maximum limit of the network. How do I know what the limits are? Well, I know this. I've established this in my lab tests. So I can check the network. If the network is well below the limit, I know that it will work well for 1588. And also you can have monitoring systems that are deployed into the network to monitor using probes and monitoring system and management system to monitor against those parameters to make sure the network is delivering sync according to the SLAs. So let's summarize the 5 steps to a successful deployment of 1588 for LTE. First, determine the synchronization requirements and the relevant ITU-T models. Do you need frequency only, or do you need frequency plus phase and time? Second, check your network today. Characterizing the mobile backhaul network that you have today is vital because A, it helps you characterize the network, but B, it helps you determine whether or not LTE is going to work before you expensively deploy the systems. And then you move to the lab. The lab tests are vital because it tells you beforehand if the thing is going to work, but more importantly, the lab tests help you determine pass or fail limits for your network. You then deploy the network according to the ITU-T guidelines, and you can test, monitor, and probe against these SLA limits that you've established back in step 3. Calnex Solutions has been the world leader in testing and deploying and consulting for 1588 version 2 deployments all around the world. Please contact your local Calnex sales representative for more information. Thank you for your time.